You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Security Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Network infrastructure security models are structured frameworks for protecting networked systems and resources. They provide repeatable patterns that guide how to enforce boundaries, monitor communications, and restrict access. These models go beyond individual tools, such as firewalls or intrusion detection systems, by establishing an overall philosophy of defense. Whether an organization chooses perimeter-based approaches, segmentation-driven designs, or modern zero-trust patterns, the model defines how risks are managed at scale. Security models also shape how controls are layered, how telemetry is captured, and how enforcement adapts to different assets. They give coherence to diverse components, ensuring the network does not become a collection of ad hoc defenses. Security zones and trust boundaries are fundamental to any network design. A zone is a defined area of the network with a specific trust level, such as an internal LAN, a demilitarized zone, DMZ, or a public-facing subnet. Trust boundaries separate these zones, marking where assumptions about trust change. For example, a firewall between the DMZ and the internal network enforces policies at the trust boundary. This concept ensures that controls are placed where they matter most, at the points where data crosses from less trusted to more trusted areas. Zones and boundaries give structure to policies, preventing implicit trust from spreading unchecked. Perimeter-focused models represent the traditional approach to network defense. They emphasize strong protections at the outer edge of the network, assuming that internal systems can largely be trusted once inside. Firewalls, intrusion detection systems, and VPN gateways were historically concentrated at these choke points. While this approach provided clarity and simplified management, it assumed that threats came primarily from outside the network. In modern contexts, perimeter-only models are insufficient, as insider threats, cloud services, and mobile devices blur boundaries. However, perimeter defenses remain valuable, serving as one layer in broader models that include segmentation and zero-trust principles. Zero-trust-influenced principles challenge the assumption of trusted internal networks. Instead, they emphasize continuous verification of users, devices, and applications, regardless of location. Access is granted based on context, identity, and posture, not network position alone. In this model, simply being on the internal network does not equate to trust. Zero-trust approaches rely on strong authentication, encryption, segmentation, and monitoring. While often seen as radical departures from perimeter-focused thinking, they are best understood as extensions of defense in depth. Zero-trust models recognize that compromise is inevitable, so architectures must minimize implicit trust and validate every request. Segmented network models divide infrastructures into smaller, isolated segments to reduce lateral movement. Techniques such as VLANs, VRFs, and subnetting enable administrators to create boundaries within the network, ensuring that compromise in one area does not grant free access to others. For example, placing finance systems in their own subnet prevents attackers who breach a workstation VLAN from immediately accessing sensitive databases. Segmentation also improves monitoring by making unusual traffic between zones easier to detect. These models reflect the principle of containment. Even if attackers succeed in breaching one area, they face additional barriers before reaching critical systems. Role-based network segmentation isolates classes of services based on their function or sensitivity. Instead of segmenting solely by physical or logical location, networks are divided by role. Databases in one segment, application servers in another, and end-user devices in their own. This approach ensures policies align with service function. For instance, databases should only communicate with application servers, not with workstations directly. Role-based segmentation simplifies rule sets and reduces exposure, since only necessary flows are permitted. It turns network segmentation into a business-aligned process, mapping technical boundaries directly to operational needs and security priorities. Choke points are centralized locations where enforcement occurs, such as firewalls, proxies, or secure gateways. They serve as bottlenecks that all relevant traffic must pass through, ensuring monitoring and controls cannot be bypassed easily. By concentrating enforcement, organizations gain visibility and simplify policy application. Choke points also allow for deeper inspection of traffic, as resources can be focused on fewer locations rather than spread thin across the network. However, over-reliance on single choke points creates risks of bottlenecks or single points of failure. Effective models place them strategically, balancing enforcement, performance, and resilience across the infrastructure. Management plane separation is another critical element in secure network models. Administrative interfaces, such as switch consoles, router management portals, or firewall dashboards, must be isolated from the data plane. This ensures that attackers cannot reach them through regular network flows. Ideally, management traffic is restricted to out-of-band networks or dedicated subnets, accessible only by authorized staff. Multi-factor authentication, encryption, and logging should be enforced rigorously. By separating the management plane, organizations ensure that even if attackers compromise data plane flows, they cannot easily tamper with configurations or disable controls. This structural separation reinforces resilience at the administrative level. Network Access Control (NAC) enforces device posture before granting network access. Instead of assuming every device is safe, NAC checks whether it meets security requirements, such as having updated patches, antivirus, and proper configurations. Devices failing posture checks may be quarantined into restricted segments or denied access entirely. NAC extends trust boundaries down to the endpoint level, ensuring that only compliant devices can communicate. This control is especially important in modern environments, with bring your own device (BYOD) practices, and IoT. NAC transforms admission from a binary yes-no decision into a conditional, policy-driven enforcement mechanism, enhancing resilience across diverse device populations. Least exposure configurations apply to both edge and internal devices. Network models should disable unused services, close unnecessary ports, and minimize administrative pathways. For instance, routers should not expose web management interfaces externally, and internal firewalls should only allow required flows. This principle reduces the attack surface by ensuring devices do only what they must, nothing more. Applying least exposure consistently across infrastructure reflects a broader hardening mindset. The fewer features exposed, the fewer opportunities attackers have to exploit them. This principle integrates seamlessly with segmentation and zero trust, creating leaner, more defensible network environments. Telemetry placement ensures that monitoring tools capture the right data at the right points. Network taps, span ports, and collectors must be placed at choke points, trust boundaries, and high-value segments. Without thoughtful placement, blind spots appear where attackers can move undetected. Telemetry collection must also scale with encrypted traffic, requiring careful choices about where and how to capture metadata. Strategic telemetry placement ensures that models are not just designed but observable in practice. Visibility is the foundation of response. Without it, enforcement remains theoretical. Models must always pair structural controls with observability to deliver actionable defense. Ultimately, network models must be chosen based on organizational risk, scale, and operational constraints. A small business may rely heavily on perimeter defenses, while a large enterprise may adopt zero trust and microsegmentation to reflect greater complexity. Regulatory requirements, budget, and staffing also shape feasible models. No single model fits all environments, but each provides patterns for reducing risk and aligning controls with goals. The effectiveness of a model depends less on its theoretical design and more on how consistently it is implemented, monitored, and maintained. The right model matches security architecture to business realities, For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Microsegmentation refines segmentation by enforcing isolation at a much more granular level. Instead of segmenting networks into broad VLANs or subnets, microsegmentation applies policies to individual workloads, applications, or even processes. This ensures that even systems in the same subnet cannot communicate unless explicitly authorized. For example, two application servers might sit side by side but remain unable to exchange data without policy approval. Microsegmentation reduces lateral movement opportunities dramatically, aligning with zero-trust principles. While complex to design and manage, it gives organizations precise control over internal communications. It represents the shift from perimeter-only thinking to internal, workload-centric defense strategies. Service segmentation patterns focus on controlling east-west traffic within data centers and cloud environments. East-west traffic refers to lateral communication between workloads, as opposed to north-south flows that cross perimeter boundaries. In modern architectures, east-west traffic dominates, making it a priority for monitoring and enforcement. Service segmentation uses firewalls, gateways, or microsegmentation to filter traffic between application tiers, containers, or services. By restricting communication to only what is necessary, it prevents attackers from leveraging one compromised service to infiltrate others. Service segmentation is critical in cloud-native and microservices architectures, where inter-service communication grows exponentially. Encrypted traffic considerations present trade-offs between confidentiality and visibility. As more network traffic uses TLS, traditional monitoring tools lose visibility into payloads. While encryption is essential for protecting data in transit, it complicates inspection for malicious content. Network models must address this by deploying decryption proxies, TLS inspection gateways, or by focusing on metadata and behavioral analytics. Decisions about where to inspect, what to decrypt, and how to manage certificates become architectural choices. Balancing privacy, compliance, and detection is difficult but essential. Effective models treat encryption as both a necessity and a monitoring challenge, designing solutions that preserve both. Application-aware gateways and proxies enhance visibility by inspecting protocols at the application layer. Traditional firewalls may filter ports and IPs, but application-aware devices can parse HTTP, DNS, or database queries, applying security rules with far greater context. For example, a proxy might block SQL injection attempts or filter malicious file uploads. These gateways integrate security directly into application flows, ensuring that threats hidden in legitimate traffic are still caught. Application awareness strengthens models by aligning enforcement with business-level logic, not just raw network flows. It acknowledges that many modern attacks exploit application layer weaknesses rather than network protocols alone. Redundancy and resilience patterns ensure that network security appliances themselves do not become single points of failure. Firewalls, intrusion prevention systems, and proxies must be deployed in high-availability pairs or clusters, with failover capabilities in place. Load balancing distributes traffic, preventing overload during peak times. Redundancy ensures that security is never sacrificed for availability. Appliances can fail without opening uncontrolled pathways. Resilient models plan for both hardware and software failures, ensuring enforcement remains continuous. This reinforces the idea that security controls must be as fault-tolerant as the systems they protect. Redundancy transforms critical choke points into reliable, always-on defenses. Policy orchestration tools bring consistency to distributed networks. Modern environments often span data centers, branch offices, and cloud platforms. Without orchestration, policies become fragmented, leading to inconsistent enforcement. Tools such as software-defined networking, SDN controllers, or cloud security posture management platforms centralize policy creation and push it consistently across environments. This ensures that rules align globally while still allowing local customization. Orchestration reduces human error, simplifies audits, and speeds response to new threats. In security models, orchestration represents the glue that binds diverse enforcement points together, ensuring architecture remains coherent even in sprawling, multi-environment infrastructures. Integrating identity with network controls enhances contextual decision-making. Instead of basing access purely on IP addresses or subnets, identity-aware models evaluate who the user is, what device they are using, and what posture that device maintains. This aligns network enforcement with zero-trust principles, requiring explicit authentication and validation at every step. For example, a contractor's device may access only specific applications, while an employee with a compliant device may receive broader access. Identity integration makes policies more dynamic, reducing reliance on static rules and improving adaptability. Models that tie access to identity achieve both precision and flexibility in enforcement. Continuous validation ensures that network controls remain effective over time. This involves routine scanning, vulnerability testing, and policy verification. Just as attackers probe for weaknesses, defenders must actively test their own enforcement. Continuous validation identifies misconfigurations, drift, and gaps introduced by updates or new services. It transforms enforcement from static defenses into active assurance, ensuring models remain aligned with intent. Validation also supports compliance efforts, demonstrating that controls are not only designed but proven. Security models that lack continuous validation degrade over time, while those that embrace it remain resilient and trustworthy in changing environments. Change control and configuration management bring discipline to network security settings. Every modification to firewalls, ACLs, or routers must be tracked, reviewed, and approved. Configuration drift or undocumented changes introduce vulnerabilities silently. By tying network changes to formal processes, organizations reduce the risk of errors while improving accountability. Automated configuration management systems enforce baselines and alert when deviations occur. This ensures that models remain coherent and consistent even as networks evolve. Change control and configuration discipline turn architectural designs into living systems, ensuring security is not compromised by ad hoc or poorly managed adjustments. Documenting network security models and enforcement points provides clarity for both operations and audits. Diagrams that highlight zones, choke points, segmentation, and telemetry placement ensure teams understand how architecture works in practice. Documentation also provides forensic roadmaps during incidents, showing responders where to investigate. Without documentation, networks become opaque, and controls drift from their intended design. Detailed records allow organizations to maintain resilience through staff turnover, audits, and system migrations. Documentation reinforces architecture as a practical reality, not just a conceptual model. It ensures security is visible, repeatable, and defensible over the long term. Ultimately, effective network security models combine architecture, policy, and monitoring. Architecture provides the structure zones, boundaries, segmentation, and choke points. Policy defines how access, identity, and flows should be managed. Monitoring ensures visibility, detection, and validation across the model. None of these elements are sufficient on their own, but together they create resilient defenses. Security models succeed when they are tailored to organizational risks, tested continuously, and documented thoroughly. They turn abstract principles into enforceable practices, ensuring networks remain both functional and secure. Models that balance these elements enable organizations to defend confidently in a complex threat landscape. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.